Good day, everyone. This is Professor Friday coming at you one more time. Today we're going to be talking about power series representations of functions, as well as differentiation and integration. So, task for today, we're going to find a power series representation of the indefinite integral of x squared times the natural log of 1 plus x times dx. We're also going to find its interval of convergence. So, the place we're going to start is with a little bit of theory. We're going to talk about the operations that can be done to a power series that won't necessarily change the radius of convergence for the interval of convergence. So these are some operations we can do. One of which we can multiply or divide by a constant. We can, this one's a good one, multiply or divide by a power of x. And we can also differentiate or integrate. Now, when it comes to differentiation, though, there's usually no big deal there. But as far as integration is concerned, we will usually need to find ourselves the constant of integration associated with it, based on whatever function we wind up with. So, based on the structure of the original integrand up here, I'm going to say let's actually start right about here. Reason being, I know that I can integrate this thing, I know that I can multiply by a power of x, but I don't see any operations here that involve a natural log. So what we're going to try to do is come up with the power series representation of the natural log of 1 plus x first. Now, as far as all of the power series representations we know, this is the place that we start. At 1 over 1 minus x, this is equal to power series n equals 0 to infinity of simply x raised to the n power. So this looks a lot like 1 plus x squared plus x cubed and so forth and so on. The interval of convergence for this thing is from -1 to +1. Now I notice though up here that we have the natural log of 1 plus x, so I'd like to alter this into a 1 plus x, and the way that we're going to do so is by claiming that 1 plus x is the same as 1 minus negative x. Reason being, as long as this takes on the structure 1 over 1 minus something, we can use this geometric series representation, or since we have an x in here, that geometric series representation becomes a power series representation. So this will be negative x raised to the nth power. So this would be like 1 minus x plus x squared minus x cubed and so forth. And the fact that we have changed that from positive x to negative x means that the interval of convergence would just get multiplied by -1. So -1 would become +1, and +1 would become -1, and outside of that, the interval of convergence does not change. Now, what I'm going to do is come up with the power series representation of the natural log of 1 plus x by taking what we just got and integrating it. The integral of 1 over something like 1 plus x would become the natural log of that, which means that we need to integrate our power series representation. So the integral from n equals 0 to infinity of -x raised to the nth power dx. Now what we could also do is point out that if we go through term by term, that things should work out pretty well. So we'll actually represent this two different ways. We'll do the term by term over here, and we'll do what it becomes in terms of the power series down here. So 1 would become x, -x would become minus x squared over 2. Then we get a plus x cubed over 3 minus x to the 4th over 4 plus ... And something important to point out is we need a constant of integration. Normally a constant of integration would go at the end of whatever our expression is, but our expression never ends. So we'll throw it up front. We'll call that C. So essentially what has happened is we've got our constant of integration plus. Let's start this bad boy at n equals 0. We'll go to infinity. We'll still have that negative 1 raised to the n power. We're going to separate that out. Notice that the power series representation still starts with a plus, so that n equals 0 is going to give us a positive. And then beyond that, n equals 1, n equals 2, n equals 3, we'll get the appropriate minus signs. The power of x that I see in each of these has increased by 1. And we've also divided by that brand spanking new power, like so. Now, a couple things that I want to point out here. The interval of convergence should not have, the radius of convergence should not have changed. But the interval of convergence could have changed in the sense that the endpoints could have changed. So we're going to call that negative 1 to positive 1, but we're not sure whether or not it converges at each of its endpoints. The other thing I'd like to do is have us plug in x equals 0 to solve for that constant of integration. So the left-hand side would become the natural log of 1 plus 0. And going based off of this expression up here, we're going to see c plus 0 minus 0 plus 0 minus 0, and there are just going to be a whole bunch of zeros. So that constant of integration is going to be the natural log of 1, better known as 0. So constant of integration goes away, and we now have that the natural log of 1 plus x as a power series is going to be the sum from n equals 0 to infinity of negative 1 to the nth power times x raised to the n plus 1 power all over n plus 1. So that takes care of our natural log of 1 plus x. What we're going to do now is start a new sheet. I'm going to recopy what I just did here at the top of this sheet. Great thing about YouTube is if you need to check back, you can always rewind. Because Lord knows I don't tell my students enough that I enjoy repeating myself. Come to think of it, I have told my students pretty frequently that I enjoy repeating myself. I also find myself pretty frequently repeating myself. Pause for laughter. Alright, back to reality. So, as a quick reminder of what we're supposed to be doing with this, on our previous sheet, we are supposed to be finding the indefinite integral of x squared times the natural log of 1 plus x. Well, now I have the natural log of 1 plus x. I'm going to multiply that bad boy by x squared. So x squared times the natural log of 1 plus x is going to be equal to power series representation of the natural log. And we're going to go ahead and multiply that thing by x squared. Now with that in mind, x squared contains no n's, so as far as the series is concerned, that thing might as well be a constant. It can be moved in or out of the summation. So n equals 0 to infinity. Now we've already got an x raised to the n plus 1 power inside here. If I were to multiply that by x squared, I can add together the exponents. We'll call that n plus 1 plus 2, which will be n plus 3. So x raised to the n plus 1 times x squared give us x raised to the n plus 1 plus 2 power, which then got simplified. We are now ready to integrate this thing. Just for clarity though, I want to write out the first few terms of what this thing looks like. At n equals 0, we would get positive 1 x cubed over 1. At n equals 1, we would get negative x to the 4th over 2. Plugging in n equals 2, this would be plus x to the 5th over 3. And by this point, hopefully, you're starting to see the same sort of pattern that I am. Alright, so once again, we will integrate this two different ways. We'll go power series representation and we'll go term by term. So x squared times the natural log of 1 plus x dx will be the integral of this power series representation, n equals 0 to infinity, negative 1 to the nth power, x to the n plus 3 power over n plus 1 dx. So again, we'll do this two different ways. We'll integrate up here, and we'll integrate the power series representation. X cubed will become x to the 4th over 4 minus, we get an x to the 5th over 2 times 5, x to the 6th over 3 times 6, and x to the 7th over 4 times 7. And of course, we get that second constant of integration in here. I'm going to reuse that c. So let's see what happened. Power of x went up by 1, and we divided by the new power. So all that happened, once again, was the power rule. N equals 0 to infinity, negative 1 raised to the n power times. Power of x goes up by 1, giving us n plus 4. The n plus 1 that was in the denominator will stay in the denominator, and we'll divide by the new power. Division by the new power, of course, is like multiplication by 1 over that power, so that'll show up in the denominator. Now that completes the expression that we were looking for. What we don't know, though, is whether or not it converges at its two endpoints. So what we're going to do is test the two endpoints and see if it converges at those. I'd like to start with x equals 1. So starting with x equals 1, the power series representation, we're going to not worry about the plus c for just a moment because it's really not going to have any sort of impact in here. Those will be negative 1 to the n power times 1 to the n plus 4 power all over n plus 1 times n plus 4. 1 raised to any power, though, is just going to give us the very same. So this would be negative 1 to the nth power over n plus 1 times n plus 4. When we take a look at this, we're going to tell ourselves we are comparing this to something in an attempt to figure out whether or not this thing converges. You could use the alternating series test. That would work just fine. I noticed that your denominator, though, is going to wind up with an n squared, so what you could do is a comparison test to 1 over x squared, or 1 over n squared, excuse me. So possibilities, you could use the alternating series test. You could do a comparison test. Compare to the power series, or not power series, p series, 1 over n squared. Regardless of what you're going to do, you're going to find out that this converges. The other thing you could do, and this would be a bit of a shortcut, is test this for absolute convergence. Because of the n squared that's down here, I know that it's going to converge anyway. The reason that I bring that up is that we also need to check out x equals negative 1. So at x equals negative 1, we're going to wind up with negative 1 to the nth power times negative 1 to the n plus 4 power all over n plus 1 times n plus 4. After you do a little bit of work with the negative 1s, negative 1 to the n times negative 1 to the n plus 4, that would be negative 1 to the 2n plus 4 power, which, if you factor 2n plus 4, that'll be 2 times n plus 2. Well, negative 1 squared is 1, and 1 raised to any power, that's just going to be 1. So this would be 1 over n plus 1 times n plus 4. This is another situation where you can compare to the p series 1 over n squared. You're going to find out that this converges. So final answer for the interval of convergence. This now converges at both of its endpoints, -1, +1. So the interval of convergence will be the closed interval from -1 to +1. I hope you found this informative. Please feel free to watch it again if there were parts that you missed, and I hope you have a lovely day.